Hello, everybody. My name is Lucio Galeati. I'm a PhD student from the University of Bonn. And today I'm going to talk about singular distribution-dependent SDEs driven by additive fractional Brownian motion. In particular, this is joint work with Fabian Rand from University of Oslo and Avi Mayorkas from University of Oxford, and is currently in archive preprint. So the kind of equation I will focus on is of this kind. So it's called the distribution-dependent SDEs, or sometimes mean-field SDE or McKim-Vladov SDE, mostly because we have a drift, capital B here, which depends on the position at time t of the solution x, the unknown, but also on the one-time marginal, the low of the solution xt itself. And in this case, in particular, the peculiarity is that I will take the additive noise to be a fractional Brownian motion of Earth parameter h between 0 and 1. And to make things simple, I will only focus in the case in which drift B is of the form of a term which depends on the distribution on the law of the solution by a convolution type of kernel against f and the position x, another term which only depends on the position x. And both of these will be taken to be elements of a suitable Bezold type of space. In particular, we consider them to be rough coefficients if they're possibly older continuous but non-Lipschitz. So it's a regime in which it's non-trivial if uniqueness of solutions holds, or even singular. So the case alpha smaller than 0, in which it's even non-trivial how to define these equations because one cannot, in principle, pointwise evaluate f and g into any point x. So the motivations for studying this kind of equation are the following. So the most extensively studied case is when we actually take h equal to 1/2. So this becomes a standard Brownian motion. So in this case, these equations are classically connected to nonlinear Fokker-Planck PDEs and to interacting particle systems. So in particular, they're called mean field SDEs, especially because if you consider the particle system with a mean field interaction, you expect in the many particle limit to converge to a solution of this type of equation. And in particular, even if the connection to the PDE breaks down when you take h different than 1/2, it was actually shown by Kogi, Deutschel, Fritz, and Morelli, revisiting old ideas by Tanaka and Smithman, that the classical connection to the interacting particle system via the mean field limit still holds for any value of h, as long as f and g are Lipschitz continuous, or roughly speaking, of regularity C1. And finally, the other motivation why these are interesting equations to study is that when you take standard SDs, so you remove the distribution-dependent part, but you only consider the standard part, G, which only depends on the position. Even when G is singular, it is already known by the pioneering work by Catellini and Gubinelli that it's possible to give meaning to this equation for suitable regularity parameter alpha and to show uniqueness of solutions in a regularization by noise fashion. So given this preparation, I'm going to immediately present our main results. So here, D1 is going to go to the 1 buffer time distance. And the result, roughly speaking, goes as follows. So assume we consider f and g to be elements of C alpha for alpha greater than 1 minus 1/2h, where h is the Earth parameter of the noise. So observe in particular that we can always take values alpha strictly smaller than 1, so rough coefficients. We may even take alpha to be strictly negative as soon as h is strictly smaller than 1/2. Anyway, under these assumptions, it's possible to show that for any low of the initial datum x0, there exists a strong solution, which is unique both pathwise and low. So well-Poseness holds for the distribution-dependent SDE. And moreover, we do have stability estimates with respect to the data of the problem. So if you actually consider two different sets of vector fields f and g and two different initial distributions, mu01 and mu02, we may control uniformly in time for t belonging to 0 capital T, which is a fixed finite time interval. We may control the distance between the two respective solutions to the two equations by the data of the problem. So the distance between the two initial distributions and the alpha Holder, the Bezold norm of the different vector fields. In particular, we also have a more, in a sense, more refined estimate. Whenever you take two solutions which are defined on the same probability space and with respect to the same fractional Brownian motion, we may rewrite the stability estimate in the following way. This is also a byproduct of our proof. And okay, here for simplicity, I'm just taking B to be of the form F convolutional mu plus G, but the results hold also for a more general class of traits if you check the paper. And the idea of the strategy to get this result, roughly speaking, goes as follows. So first of all, observe that assume you are given a solution X to the distribution dependent SD, then okay, if you define vector field B mu as F convolved with mu T, where mu is the law of the solution itself plus G, then necessarily by definition, X will also solve a standard SD driven by the drift B mu. So the key point, this reformulation of the problem allows to set up a fixed point argument, because the idea is like, okay, assume you already have a flow of measures, mu t, indexed by t in 0 capital T. To this, we can associate a drift b mu, defined as before. Now, with respect to this drift, we may now solve the standard SD associated, which gives us a new process xt, which in turn gives us a new flow of measures, mu tilde t, given by the one-time marginals of this process. And so this overall sets up a fixed point map. And okay, X is going to be actually a solution to the distribution-dependent SD, if and only if it corresponds to the fixed point of this map. And so existence and uniqueness of fixed points can now be checked by contractivity, or if you want, by Banach-Cacciopoli theorem. And okay, I will not have enough time to go deep into this, but the good news about all of these arguments is that solving at least the standard SD part of the problem, which does not mean checking contractivity, so way lower order of magnitude of problem, is something already available in the literature. So it was shown by Catania and Gubinelli that, for instance, if you take drifts B, which belong to C alpha, for alpha greater than 1 minus 1 over 2H, as before, then the standard SD of this form actually does have well-posedness, does have a strong existence and pathwise uniqueness for any initial datum x0. And actually, one can even check path by path uniqueness. Okay, here for simplicity, B is an autonomous drift, but the same result holds for suitable time-dependent drifts, which is something we also revisited in another paper with Massimiliano. And okay, the time regularity part of the coefficients gets a bit technical, because one has to discriminate slightly between the case in which the Earth parameter h is greater than 1/2 or h is smaller or equal than 1/2. So from now on, I will work with drift B, which satisfies this assumption, which is a bit technical. But the common denominator is that you always have spatially a regularity C alpha, which is roughly speaking greater than 1 minus 1 over 2h. And I can now present the second main result of our work, which is a stability estimate for standard SDs driven by fractional Brownian motion. Again, with rough or singular coefficients, keep in mind. And this second result is actually the main tool we use to actually establish contractivity and therefore establish the first result I presented about well-posedness and stability estimates for the DDSD. So in this case, if we consider two different drifts BI, satisfying the assumption before, depending on the choice of the parameter h, then for each of these, we do know that there exists a unique strong solution. And what we establish is, again, a stability estimate in which the difference between the two solutions, actually not just in the uniform norm, but in a suitable gamma Euler norm, may be controlled in the LP moment by the difference between the two initial datum, x01 and x02, and the difference between the two drifts. So here, the relevant points are the following. So I didn't have time to explain what is the proper meaning to give to this equation when alpha is strictly smaller than 0. The good news is this stability estimate allows to show that these solutions are the unique limit of smooth ones. So even if I couldn't tell you how to make sense of this, at least one can say, okay, if I first modify my drift, so solve the equation with modified drift, which I always can do, and then take the limit as epsilon goes, the modification goes to 0, then actually what I will converge is exactly to this object, which is what I define to be the solution. So the second key point is that here, the stability estimate is in the alpha minus 1 norm, which is a weaker norm than the alpha norm. And this is also really good news. This is really something we actually use crucially in our actual estimates to establish contractivity and then solve the DDSD. And finally, these stability estimates can be used to numerically simulate singular SDEs. So the idea is that since the drift is singular, you cannot easily set up an Euler-Majorana scheme, for instance, because you just cannot pointwise evaluate your drift. But what you can do is, as mentioned before, basically introduce a new error. So to say, I first modify my drift, and then I apply the numerical scheme to the modified drift. This stability estimate will allow you control the first error you introduce by modifying. And then for the second part, you need to apply standard or even non-standard, but numerical results, basically. And let me finish by pointing out some open problems and future directions. So as already mentioned, when f and g are Lipschitz continuous, this distribution dependent as is also rise naturally as mean field limits. So the natural question is like, is this connection, is this mean field limit also true in the non-Lipschitz case? This is currently an open problem. We do not know in the case H different than 1/2 how to address it. And this is also related to the fact that classical stochastic calculus is not available for H different than 1/2, because fractional Brownian motion is not Markovian nor semi-Martingale. So also the connection to a standard PDE breaks down, which begs the question like, can we still find some generalized connections to some kind of generalized PDE? This is also not a problem. So a bit of a more technical one, our results are stabilities in the Wasserstein norm. So quite naturally, one could ask, can we actually use the total variation instead? And finally, let me mention there are several recent works which use the stochastic swing lemma, which was first introduced by Coalet, some of which also apply to singular SDEs driven by fractional Brownian motion. So a natural future direction of research will be, can this new tool, the stochastic swing lemma, also allow to answer some of these problems? And with this, I will conclude. Thank you very much for listening. And this is a short list of essential bibliography. Thank you.